This video is going to discuss limits at a point. Before we discuss limits at a point formally, we actually need to discuss a property of a function called continuity. Okay, the adjective form we would say is that a function is continuous or it is discontinuous, and what a continuous function looks like. There are more formal ways of talking about this, but to us, in the most basic sense, a continuous function is one that can be drawn so that it contains no holes, gaps, or jumps. Okay, it should appear to be a smooth curve, and so traditionally when we talk about a continuous function is you should be able to take, if you have a writing utensil, you should be able to take your writing utensil and trace along the function without lifting or stopping your pen or paper or pencil. Okay, so just some examples. A continuous function might look like a polynomial function. So here we have a polynomial function, degree 4, possibly, or more. So that would be an example of a continuous function. We might even say a continuous function is the log function, because again, I can take it and draw it without lifting my pen. Okay, even an absolute value graph. Okay, I did stop there, but I could make one solid motion with it. Something that would be an example of a discontinuous graph is a certain type of a piecewise function. So if we have a piecewise function, maybe that looks like this. Okay, so I have to stop, I'd have to lift my pencil, and then start off down here again. This would be a jump discontinuity. A gap would be there's missing values. So a jump is vertical, a gap is horizontal, same idea. The other type is that there might be a removable discontinuity. So it would look something like this. We'd have a hole here, maybe that point is at the origin, and then we come back down and it looks something like that. So that point, we'd have to lift our pencil up to get to that extra point. So just ideas of continuous versus discontinuous. Okay, so in general, limits at a point, if we're taking the limit of a constant, we're just going to get the constant. But we actually get a nice property of limits if we have that continuous function, if we have that continuous property. Okay, if the function is continuous, okay, so we have to have that continuous, so we have to think of the graph in our head, or we have to know what type of function it is. And we also have to have the value c, so that limit value has to be in the domain of f. Okay, so it has to be in the domain of f. Then we can directly substitute it into the function and get out our result. Alright, so first example we have is limit as x approaches 2 of the natural log of x minus 1. Okay, x minus 1, or natural log of x minus 1 has a domain of 1 to infinity. So it is okay to put this value right into the limit. So I can say that this is equal to the natural log of 2 minus 1. Okay, and evaluating this, I just get 0. So it would be natural log of 1, which is just 0. Next example, limit as x approaches minus 3 of 1 plus e to the negative x. Alright, so e to the x has a domain of all real numbers. 1 has a domain of all real numbers, so I can directly substitute in minus 3. Okay, minus 3, I'd get 1 plus e, and then be a minus of a minus 3. I'll just show that here. So my answer would be 1 plus e to the third. Alright, this next one, limit as x approaches 3 of 2x minus 6 over x squared minus 9. If I factor this denominator, this is x minus 3 and x plus 3. So if I substitute in 3, that actually creates a problem because that would make my denominator 0, and therefore 3 would not be in the domain. Before we give up though, let's try some algebra. So I am going to factor both the numerator and denominator. So limit as x approaches 3. Okay, so again, remember you need this notation if you have not yet evaluated the limit. Factoring the numerator, I would get 2 times the quantity x minus 3. Denominator is x minus 3 times the quantity x plus 3. Okay, then I can simplify. X minus 3's end up canceling, and this would be equal to the limit as x approaches 3 of 2 over x plus 3. And now this I can work with because I can put in 3. 3 is in the domain of this new function, and I would get out 2 over 3 plus 3, which is 6, so 1/3. Again, so just to reiterate, before we give up, we can put in, or we can try factoring, do some algebra. Another way you could also do, if you think that the limit value is not going to work, is remember in the video that I made on the limit and the limiting process, there were actually 3 ways of doing this. We could either look at a table, so make a table of values coming from either side, table coming from either side of 3, or make a graph and look at the graph. Okay, so other options exist. Algebraically is often the fastest, but just know that you can do others as well. Alright, so now we're going to encounter instances where we actually have limits where if we were to use the direct substitution property, it would fail because, again, the limit value might not be in the domain of the function. So in that case, we're going to introduce left and right hand limits. And these are going to help us get around the issue where the limit value is not in the domain of the function. So a left hand limit, all it means is that we're taking the limit as we come in from the left, hence left hand, and seeing what that approaches, and then the right hand limit does the opposite, just coming in from the right towards the value. Now notationally, you'll notice that the limit actually, the notation changes, so it's limit as x approaches that limiting value with a superscript of minus for the left. So left, there's a minus sign there. For the right, again, you'd see a plus instead. Now, to find these, really the only way that exists is we have to do these numerically. So we would have to make table of values that approach the limit from either side. So again, I'm using the function from above. So in the case of, if this was 0, so c is 0, in this case, I would have to take values leading up to 0 and see the trend that f of x progresses towards. Okay, and again, for the right hand limit, I would take values coming in from the right, getting close to my value, so 0 in this case, and look at the value and look at the trend that happens in f of x. In both of these cases, it looks to be that they approach infinity, or they grow without bound. Okay, so now we get this nice property or theorem out of all this, and it is that if the left and right hand limits approach the same value L, okay, typically L should be finite, okay, so we're gonna discuss about this in just a minute. But if they approach the same value, or they have the same limit, then we can say that the limit for the original function has that value. So that's this statement down here. So if the left and the right hand limit are both the same value, then that means that the limit itself, looking from either direction, is just L. So we would say that the limit as x approaches 0, instead of left or right, would be infinity. Now again, the limit value has to be finite, but we can also say that, okay, it grows without bound, and infinity is just a way of communicating that. Okay, one important note that I'll make here is that in order for us to conclude that the value of the overall limit, so limit coming from both sides, the two-sided limit, exists, is that the left and right hand limit agree. If they do not approach the same value, if they do not agree, then the limit does not exist most certainly. Okay, so for example, if you were to take the limit as x approaches 0 of just 1 over x, that one you would see does not exist, and I encourage you to do that on your own time. Alright, so now limits, we may also be able to determine these graphically. And so here's an example. We're just going to run through this quick. So we want to determine the value of each of the expressions down here. So as the limit as x approaches minus 2 from the left, what is that? So again, from the left, I come in from the left-hand side. So I start over here, come down here, follow the function, trace along the function, and when I hit negative 2, I stop. Okay, so negative 2, I got stuck here, and so that value is minus 3. Coming in from the right, so again I would start over here, trace along the function, and then I would jump up. Okay, minus 2, minus 2, minus 2. I get stuck here, so even though I do not have a point there, I get stuck. Okay, also the limit value does not have to, the function value does not have to exist for you to have a limit. So for example, we saw here that, okay, we had the function value at minus 3, that was okay. Here, we actually had a limit value even though we did not have a function value. Alright, progressing on here. The limit as x approaches 2, and so then from these two, if we were to look at the limit as x approaches minus 2 of f of x, we would actually say that that does not exist because the left and the right hand limits do not agree. Running through these other ones, 2 from the left, so again I trace along the function, get stuck at 2, come in from the right, and I get stuck down at minus 4. Okay, f of 2 is 0, and f of 4, this is actually an interesting one. So f of 4, you'll notice that there's a horizontal line here. This would continue on. So actually, this is an entire interval. This is 4 to infinity. So the function would attain, sorry, I have that backwards. Let me erase that. I was looking at the y values and not the, right, so I want to know when x is 4, what is the y value, and I was looking at the opposite way around. So 4, y is 4. Okay, and that is a brief overview of limits at a point.